Chapter 11 is all about area, and today we'll be reviewing some old area formulas that I'm sure you've seen before. We know that area is measured in square units, so to find area just means to find how many squares would cover a shape, which is super easy to do with a rectangle. And since this is a 6 by 2 rectangle, it seems pretty obvious that we would be able to fit 12 squares inside. And the area for a rectangle is just base times height or length times width because of that. Well, for a parallelogram that has a base of 6 and a height, like straight up and down height of 2, it's going to have a longer side length, but that doesn't matter much because a parallelogram has basically the same area as a rectangle with the same dimensions. Every parallelogram can just have that one triangle slid over and it'll turn into a rectangle with the same base and height dimensions. So we can also say that the area of a parallelogram is base times height, remembering that that height is the straight up and down perpendicular height. You probably remember that a triangle area formula is just 1/2 base times height, which is also related to a rectangle / parallelogram. If we compare a triangle to a parallelogram with the same base length and same height, can you see that there would actually be room for 2 of those blue triangles in this parallelogram? And that's true for any triangle. Any triangle, if you take 2 of them and flip them around, stick them together, you would be able to make a parallelogram. So if the area of the parallelogram is base times height, and the triangle is only half as big, 1/2 base times height would make sense. And the base of the triangle is just this 12 feet. The 6 feet is not even really necessary, except for it might be useful to find the height, because did you notice that we don't know how big the height is? We know that this side is 7 feet long, but we're looking for like watermelon dropping height, altitude, when we find the area of a triangle. The key here is that we know the 7 and we know the 6, so there's actually a formula that helps us find that height, and it's just the Pythagorean theorem. So we can say that x squared plus 6 squared equals 7 squared. And we find out that the height then must be the square root of 13, which is 3.605551275, but I would rather not use the decimal version of that height and just leave it as square root of 13 until the very end. That's something that I want you to learn this chapter, is that we don't want to do any rounding until we get to the very final answer. So to finish this example, we're going to take area being 1/2 base times height, and we're leaving that in its radical form. Now, if we would have used the entire 18, then we would have been finding the area of this whole thing. So if I'm just looking for the area of the shaded blue part, I only use the 12 feet as the base. And now when I type in 1/2 times 12 times the square root of 13, I can just type all of that in at once and I get 21.6333, which I think I'll round to the nearest hundredth this time. And since that's an area, squarea, we're talking about square feet. We could fit 21 of these little squares in this blue triangle. I'm sure you've seen the trapezoid area before. It's kind of complicated. 1/2 base 1 plus base 2 times the height. But have you ever wondered why that works? Well, I'm going to duplicate this trapezoid and flip it around, and what shape does it make? A big old parallelogram. Everything's related to a parallelogram. And because I flipped this upside down, this would be 4 and this would be 8. So if I were finding the area of the big parallelogram, I would take base times height, and the base would be 12 units long because I'd have to add those together. Which is totally what's going on in that formula, right? Adding those two bases together gives us this total base of that parallelogram. So I've got the base times the height. What's up with the 1/2? Remember, I didn't want the whole parallelogram, I just wanted a trapezoid. So I only wanted the area of half of that shape. Another way I could explain this formula is by taking these little triangles off the bottom of the trapezoid and flipping them up to the top. So the area of the trapezoid is actually equal to the area of this rectangle. And we know how to find area of rectangle, just base times height. I know that the height is that 5 inches, but how long is the base now that I've cut off those little triangles? Well, it happens to be the length of this segment in the middle. That segment in the middle was called the mid-segment, and we knew how to find the length of that. Do you remember? It's just the average of the bases of the trapezoid. So we could just take 4 plus 8 and divide by 2, and we would know how long this mid-segment is. And again, the mid-segment is the width of that rectangle. And now check it out. Do you see the comparison between this and this? We just did 1/2 the bases added together, right? We did base plus base divided by 2. And all along we were planning on taking that length times the height. So there's the height part. So that's just two different ways that I can explain where that formula comes from. Let's actually use the formula and see what the answer would be. Area equals 1/2 base 1 plus base 2. Remember, for just the trapezoid, that's the 4 and the 8. Times the height, which is the straight up and down height. We actually don't need the length of these slanty parts to find the area. So I'm getting 1/2 times 12 times 5. We don't distribute that 1/2, it's one or the other. Should I half the 12 or half the 5? Up to you. I think I'll half the 12 because that seems easier to me. Or really, you could just type this all into your calculator at once. As long as you use those parentheses, you should also get 30, and the answer is 30 square inches. We could fit 30 little squares into that trapezoid. There are actually two possible formulas that you could use for a rhombus. Remember that a rhombus is a special type of parallelogram. So if you happen to know the base and the height, you can just use the parallelogram area formula. And we could do that on this first example because the base is 5 and the height is not 5, right? The height would be that watermelon dropping height. The height is 4.8. So if you know the base and the height, you can go ahead and just use base times height for a rhombus. Now the second rhombus is also a 5 centimeter rhombus, but you'll notice that it doesn't have like a height drawn on it. If you think of this as being the base side, then we would need to know how long this little piece is in order to talk about base times height. So that's where the other formula comes in. This is another formula that you can use for all rhombuses. 1/2 diagonal 1 times diagonal 2. And when I talk about diagonals, I'm just talking about the lengths of those diagonals. If you remember the lovely symmetry of rhombuses, if that side is 4, this side is 4. And if that's 3 up there, then this would be 3 down here. So in the formula, we're going to grab the entire length of the diagonal and the entire length of the diagonal. So in this case, we would be talking about 1/2 times 8 times 6, the lengths of those two diagonals. Half of 8 is 4 times 6 is 24 square centimeters. Now we're supposed to be curious about where that formula comes from. Why does that work? And it actually has to do with triangles, which kind of makes sense because this sort of looks like a 1/2 base times height, doesn't it? And the diagonals split the rhombus into congruent triangles. So I could just add the area of those 4 triangles up, or I could even write that as 4 of that same 1/2 times 4 times 3. If I call that 4 a 2 times 2 and just do some clever rearranging, if I take that 4 from the front and just split it up into a 2 times 2, then I think you can see, do you see that that's the length of one of the diagonals, and this is the length of the other diagonal. So 1/2 diagonal 1 times diagonal 2 is just a shortcut for adding up all of those triangle formulas. And I think you can probably see that on this kite, we also have triangles formed by those little chunks of diagonal, right? So maybe not too surprising that that area formula also works for kites. 1/2 diagonal 1 times diagonal 2. And so this up and down diagonal, I would just have to add those together. 24 plus 6 is 30. 1/2 diagonal 1. And then the other diagonal, remember if this is 8, then this is also 8. So diagonal 2, I'm going to call that a length of 16. And typing that all in, I get 240 square meters. I know I write that as like meters squared, but you should never read it out loud that way. We call them square meters. Can you say that with me? Square meters. Square meters. So the point of today's lesson was that you learn all of those area formulas. and that you also understand that they pretty much all come from just that basic idea of finding the area of a rectangle.